We've come to a point in mathematics where we've been told up to this point that some things are not possible. We're going to go ahead and show you otherwise. Let's start with the square root of 4. If we type that in a calculator, we're going to get an answer of 2. If we do part B, this is the same as saying there's a negative on the outside, and the square root of 4 we said was 2. So we're going to get an answer of negative 2 in our calculator. When we try part C out, notice what the calculator does. Here's another calculator response. And other ones will tell you error, domain, etc. So up to this point in your mathematical careers, especially in Algebra 1, we would have said this was not a real solution. You may have been told error, you may have been told undefined, you may have been told a lot of different answers. However, the one that should have stuck and the one that should have been taught is that this is not a real solution. What is real? Well, in order to define real, we'll have to define imaginary or complex numbers. So what do these look like? Let's look at problem 2. Well, first up on the menu is this, right? All the calculator said this is non-real. And so if it's not real, it's complex. Any square root of a number is complex. Any even root of a negative number is complex. Anything within an imaginary unit. This is an I. Most of you make your I's like this. The mathematical I, which represents an imaginary unit, looks like this. You're going to see me write this a lot in these notes, so don't confuse this with a 2. This is an I. This is a 2. This is an I. I. This is also a complex number. So is this. And this. Or even this. The point is, a complex number has either an even root of a negative number, or it has an I, an imaginary unit. Which means everything else that you learned up to this point would be real. Your favorite value meal at the fast food. Your age. The amount of money in your bank account. The number of ex-boyfriends you have. Your favorite dessert. Etc. So this is pretty important right here. We define I, the imaginary unit, as being the same as square root of negative 1. We're going to show you some examples of that. And furthermore, if I is equal to square root of negative 1, and if I square both sides, I get that this is I squared. And over here, we get square root of negative 1 times square root of negative 1, which ends up being negative 1. And so that's why we define I squared to be equal to negative 1. So you should be able to throw these out at any given time when needed. The fact that I equals square root of negative 1, and the fact that I squared is equal to negative 1. Problem 3, square root of negative 8. So we notice that this could be broken up as square root of negative 1 times 8. And that could be broken up further as square root of negative 1 times square root of 8. But what's the square root of negative 1 by definition? That's I. The big problem now is, what the heck is square root of 8? For that, I'm going to strongly suggest that we use prime factorization trees. So pick two numbers that multiply to 8. And I'm going to suggest that once we hit a number that's prime meaning that it can only be divided by 1 in itself, circle it so we know we're done. This is prime. We can't break down 2 anymore. It would be 2 times 1, which that makes it prime. 4, we can break that down into 2 times 2. But again, these are all primes. Prime numbers are like 1, 2, 3, 5, 7, 11, etc. Okay. So instead of writing the 8 that we have here, I'm going to write it with these 3 numbers that I have circled. You should be comfortable with this idea because factorization trees go back to elementary school, and we're past those days. Now, and if you're still like, what's going on? What's 2 times 2? 4 times 2, 8. So that's how we got the 8. Oh, yeah. Okay. Now, the way this works out is this is a square root. Square, so that's a 2. We're looking for the square root. If you didn't know this, the square root actually has a little 2 on the outside. We just don't write it. Okay, so anytime you see this and you say square root, hint, how do you say this? X squared. That idea of squared is the same idea of square root. They're actually the opposite of each other. They're the inverse of each other. Okay, now the square root right here, we're looking for pairs. So here's a pair of 2's. And I'm going to pull that out. And it's a pair, right? One pair. So that's going to be a 2. The I is already out there. And inside we had a 2 left over, so I'm going to put that 2 right here. So what I'm saying then is the square root of negative 8 is 2i radical 2. And we're only able to do this because we have complex numbers. If you were to put this in a calculator, it'll tell you non-real solution, error, domain, etc. So you are doing math that the calculator cannot do. Let's try another one. So same idea, right? We can break this up into negative 1 times 9. And that's negative 1 times 9. And by definition, this square root of negative 1, that's an I. If we do your factor tree for 9, 9 is 3 times 3. Okay, I'm not going to do a tree for that. You can if you want, but it's the shortest tree. And again, if we pull out a pair, what do we get? 3. And there's no leftovers. So the answer is just 3i. Now, if we overdid this problem, we probably did overdo it because what's the square root of 9? It's 3. Okay? So you could have just said, okay, well, Mr. Over, I know that this negative comes out as an I, and I know the square root of 9 is 3. And then you just write it in the right order, and you're going to get 3i anyway. Here's another one. So again, you can split this up into a negative 1 and a radical 32, and the negative 1, radical negative 1 becomes an I. What we have to worry about now is this 32. We do a factor tree. Now there's no wrong way to do this as long as you can multiply. I know, for example, 4 times 8 is 32. And 4 is 2 times 2. Those are both prime numbers. 8 is 2 times 4. 2 is a prime number. 4 is 2 times 2. And those are prime numbers. So we can say that 32 is the same as saying 2 times 2 times 2 times 2 times 2. That is the prime factorization of that number. Don't trip, fam. This is elementary school. This is multiplication. We got this, okay? Now, we're looking for pairs, okay? So here's one pair of 2's, and I'm going to pull that out and count it only once. Here's another pair of 2's, and those come out here, and I'm only going to count them once. This one is so lonely, so very lonely, and it stays in there. So we end up with this so far, right? This blue 2, this green 2 came out. This sad 2 stayed in there. There was an I that we picked up from the square root of a negative 1. But what's 2 times 2? That's 4. So our final answer for this one is 4i radical 2. If you're asking, Mr. Over, where does the negative go? It became an I, right? So is negative always I? Watch out, be careful. If the negative is on the outside, then the negative is on the outside and that's it. Remember, look at problem 1 in our notes. The calculator didn't have any problem with this. It said it was negative 2. Okay. The problem is part C, where it said non-real solution error. If the negative's on the inside, it comes out as an I. But that's only if it's an even root. One last one for this video. So here's negative 169. We can split this up, of course. Oops. And that's, of course, an I. What is the square root of 169? You'll be hard-pressed to find out that. Doing a prime factorization tree is a little tricky. 169 is 13 times 13. But, silly people, that's a perfect square. So, if we square root 169, which is 13 and 13, well, there's a whole pair of 13s right there. So, if we end up taking everything out of the square root, we no longer need the square root. So, this one is going to be 13i.